Next up, Dr. Aled Roberts.
Hi everyone, so I'm Aled Roberts and I'm a research fellow at the Future Biomanufacturing Research Hub based in the Manchester Institute of Biotechnology. So my PhD was in materials chemistry, but I've since immersed myself with biologists and biochemists in the MIB. So I'm kind of like a living example of an interdisciplinary scientist. My niche is the interface of material science and biotechnology, with my background in chemistry being like the common unifying language. So today I'd like to talk about our latest interdisciplinary research project, which has just been accepted for publication. We've also filed for a patent on this. So the way we make organic molecules is changing, and it needs to change because we know we need to move away from oil-derived petrochemicals, preferably sooner rather than later. One potential alternative to traditional petrochemical-based synthesis routes is to use enzymes, which are essentially in nature's catalysts. And these can convert natural feedstocks into higher value chemicals and materials. And this is often done through the setup depicted in Figure A, and it's increasingly moving towards this type of flow biocatalysis type configuration. And here you essentially pass precursors over an enzyme that's been immobilized to a solid support, and then the precursors in contact with the enzyme will be converted into the desired product. And these enzymes generally operate under relatively benign conditions, ambient temperatures, ambient pressures, pH, and so on. However, the immobilization supports themselves are quite unsustainable. So they're typically single-use polymer microbeads, so they're literally microplastics. And they've also been chemically functionalized by relatively harsh conditions to introduce reactive chemical groups such as epoxide groups. So what we've been doing in this project is investigating natural wood as a potential sustainable alternative. So what we do is we remove the lignin from wood through like a process similar to how paper is made, so a pulping process, but relatively mild conditions. And this leaves the aligned cellulose channels of the native wood structure. And these channels are very useful because you can pass liquids through them, and the liquids will contact the surfaces, but without there being too much pressure building up, which is quite ideal for something like flow biocatalysis. So the way we immobilize the enzymes to the cellulose scaffolds is by hijacking another natural mechanism. So many proteins in nature have evolved to strongly bind to cellulose through what's known as a carbohydrate binding module, or CBM. And what we've done is to engineer these CBMs onto our enzymes of interest, as shown in Figure C. So we can then attach enzymes to the wood-derived cellulose without any further chemical modification of the cellulose itself. And Figure D shows this process with fluorescent proteins, just for visual demonstration. And we can get immobilization efficiencies as high as 97%. So almost all of the enzyme we can get attached onto the cellulose. So just in summary, we remove lignin from wood without disturbing the native porous structure. We then engineer and produce enzyme CBM hybrid constructs, then passing these through the cellulose scaffolds that become immobilized by the CBM. And then we can use it in a flow biocatalysis setup. So we pass reactants through the cellulose scaffolds, and the immobilized enzymes catalyze a chemical reaction to produce desired products. And this process is arguably relatively green and more sustainable than many of the traditional synthesis routes. So thanks very much for listening.